Hello friends, welcome to session 2 on SFD and BMD, its problems and solution techniques. Hope you have watched my session number 1, which will cover basic concepts and fundamentals of shear force and bending moment diagram. However, we will review some of them here. I want to recall those two fundamental relations what we have seen in session number 1. First is derivative of shear force is nothing but rate of loading on beam, and derivative of bending moment is nothing but shear force. Now based on these two relations, we have written the relation between loading diagram, shape of SFD and BMD, and just recall that I said when you come from loading diagram towards SFD and then towards BMD, you are going to integrate the things, and when you go from bending moment diagram towards SFD and towards loading diagram, you are getting derivatives. So let us have some recap on all these things. First is concentrated loads. Two effects are there. One is point load and couple, and you rightly seeing on the screen. Shape of SFD, sudden rise or fall when point load is there, but no effect in BMD. But when couple is acting, there is no effect on SFD, but there is sudden rise and fall in BMD. All these things we have already learned in our session number 1. Just I am taking a recap. In case of distributed load, when there is no load at all on a segment of a beam, then SFD is constant line, because no load means, as I said earlier, that 0 for 0 integration is constant. So SFD is constant line, and for constant integration is inclined line, that is sloping line. So BMD is sloping line. Similarly, in case of UDL and UVL, we have discussed everything regarding shape of SFD and BMD. One more point we have to recall that we already said that there are 2 points we have to take care of. One is point of zero shear, and whenever point of zero shear is there, the bending moment value has peak value, because we have relation that dm by dx is equal to v, and when v becomes 0, then this particular function, that is bending moment, has peak value. And second point, we have learned that point of contraflexure. That means whenever bending moment is 0 and changing its sign from sagging to hogging or vice versa, that particular point is called as point of contraflexure. Moving ahead, here are some general steps to plot SFD and BMD. So our step number 1 is draw FBD of given beam. Find support reactions by using equilibrium conditions. But important point I have to note here that whenever you draw free body diagram of given beam, we are interested only in lateral forces and couples, because these two are the only elements which will cause shear and bending. Whomsoever is the axial force, that should not be considered, because it will create only elongation and contraction of the member. So we are interested only in lateral forces and couples. Fine. In second step, we are supposed to do some SF calculations using proper sign convention. In third step, we are going to calculate BM values at various feature points. Now, which are feature points we have to consider, we will see in the next problem with again proper sign convention. And last point is to locate point of contraflexure if at all it is available in bending moment diagram. Fine. So let's move ahead. From practice point of view, let's move quickly through one more example. Consider beam ABC, where AB is overhanging portion, B and C are supported, and it carries UDL of 10 kN per meter, a couple of 80 kN meter, and uniformly varying load is acting on the beam. Okay, as we seen, the first part is to find out reactions. So draw FBD, that means I am showing reactions at B and C. As there is no horizontal load, there is no horizontal reaction at all. And even though it is present, we are not caring about horizontal, because horizontal is nothing but axial effect, and that axial effect we are not considering in our shear force and bending moment diagram. So I am showing these two reactions RB and RC, and we are applying first equilibrium condition of moment. We will take moment at point B so that reaction at C can be found immediately. So writing that equation, moment at B. So there is a UDL, so rectangular load. So UDL is 10, distance is 3. So intensity into distance is total UDL. It will act at midpoint because it is a rectangular load, and I am taking moment at point B. So this horizontal distance we require, and that is 1.5. Observe that this moment is creating anti-clockwise moment, so the sign is taken positive. Second is couple. Couple is 80, so it is taken as it is, positive because of anti-clockwise nature. Third is triangular load or uniformly varying load. We know that for triangular load, total triangular load is taken as area of the triangular portion, that is 1/2 into intensity into distance. So this is triangular load which will act at centroid of triangle. So centroid of triangle is here. From 90 degree it is 1/3 distance. So 1/3 of 6 means this becomes 2. So distance becomes 2. Observe that triangular load is creating clockwise moment about point B. So sign is taken negative. And last one is RC into distance, this distance 6. So RC into 6 is the moment about point B. It is anti-clockwise, so taken positive. Solving that equation, we will get reaction at C equal to plus 27.2. Answer is positive, means assumed arrow initially is correct. Next is summation Fy equal to 0. So applying proper equations, we are getting reaction at B is equal to positive 146.8. Again positive means assumed sense of RB initially upward, it is correct. Step number 2 is shear force calculations. And for shear force calculations, we have 3 points A, B and C. At each point we have decided already that 2 values we are going to calculate. One is just left of each point and just right of each point. So total 6 values of shear force we are supposed to calculate. Again same sign convention we are using. Sections left upward is positive, and we are considering always left FBD for our shear force calculation. So let us move one by one. The section slider we are now consider. It is like this. A left, first value. Left FBD we have considered. There is empty space. So VA left is 0. Then A right, just right of A. Again from left point to right point, there is again no point load is coming. So original value is taken and newcomer is 0. So final answer is 0. Next is B point, B left. From A left to B left. Observe there is newcomer of UDL. Intensity is 10. Distance is 3. So total UDL is 10 into 3. Acting downward means negative. So this value original is taken and newcomer is minus 10 into 3. So answer is minus 30. Next is B right, just right of B. So from B left to B right, observe that this vertical reaction comes into picture. So this value is taken as it is, and newcomer from B left to B right is vertical reaction upward, so it is positive. So final answer is 116.8. And last point is C left. We are having value of B right here. From B right to C left, observe there is UVL acting downward, so we have to take negative, and UVL means uniformly varying load. Area will be 1/2 into intensity into base. So 1/2 into 48 into 6 is the load acting downward, so sign taken is negative. So original value is taken here and newcomer is UVL. So final answer is 27.2. C left is over. Last point is C right. From C left to C right, this is the newcomer. So we have taken the value as it is, and newcomer is this vertical reaction upward. Upward is positive, so this is taken. Observe that final answer is 0. We are getting our first check. We are starting with 0 and ending with 0. So our first check is over. Now let us plot shear force diagram. as we plot for earlier example. Baseline is taken. First value is A left, it is 0. Second value is A right, it is again 0. So A left and right both values are 0 here. Next point is B. So this value we are going to plot. B left, it is minus 30. So plotted below baseline. Joining this point and this point. Observe that there is a rectangular load, that means UDL. Whenever UDL is acting on beam portion or rectangular load is acting on beam portion, SF diagram is inclined line. Sloping down because UDL is acting downward. Next point is VB but right portion. At VB right, we have sudden rise, that is 116.8. So this value is plotted. So this value is already we are having. This is new point. So joined by vertical line. Next point is C left, this one. So we are having B right. From B right, we will plot C left. So this is our C left value. Now we have to join these 2 points, B right and C left. Question is how? That's why again we will go to our fundamental concept. Whenever UVL is acting on beam portion, UVL is inclined line, SFD will be parabolic curve of second degree. Only the point of investigation is whether parabolic curve concavity up or down. So remind that table and logic. This UVL is downward and decreasing, and we know that for downward UVL decreasing, the concavity is on upper side. So this is the concavity curve having concavity at upper side. Parabolic curve second degree, concavity up. This point is now plotted. Now last point is this point, VC right. So this is VC right, and this value we are joining by vertical line. Once we plot our shear force diagram, as I said, we have to check our SFD nature. Observe that whenever UDL is acting, we say it is sloping line. Yes, it is available. Sloping down. Whenever UVL is acting, there is a second degree parabolic curve in SFD, and for decreasing downward UVL, the concavity is up. Next point to check it, whenever point load is acting, there is sudden rise or fall. For upward point load, observe that there is sudden rise. Again for upward point load, there is a sudden rise. Right? So these points we have to going to consider to check our diagram of shear force diagram. Now one point again we got here where the shear force crosses the baseline, which is called point of zero shear. So our logic is again continued. Take one section. So this is a section line I have shown, and draw freeboard diagram of either left FBD or right FBD. Here I have two choices for this section line. Either I have to consider right FBD or I have to consider left FBD to draw the section line. I think right side is simpler. So we have taken X from right. This is the X we have taken. So we have plotted the section like this. So this is our section line, and X distance is, or X section is taken from right. Now we will write bending moment equation for that right FBD. So for this right FBD, we are interested to write bending moment equation. But first of all, I have to find this height of triangle at this particular section, because I have to consider only right FBD. So by using similar triangle, I am getting that distance equal to 8 times X. So intensity of triangle at the section line is 8 times X. Now consider this particular portion and let us write the moment equation. So taking moment of all forces about the section line, force is 27.2 and distance is X. As it is bending moment, we should use sagging and hogging. So observe that this moment is like this. So it is called as out or sagging. So 27.2 into X is the positive moment of this particular force. Now moment of triangular load. This is the triangular load. Triangular load is acting downward at 1/3 from 90 degree angle. So from this end, it will be X by 3. This distance is X by 3. Right? 1/3. And triangular load is 1/2 into intensity into base. So 1/2 into intensity is 8 times X and base is X. It is acting at X by 3 distance. So this is the moment of the triangular load about the section line. Observe that triangular load is acting downward, which will create moment like this, So according to our basic fundamental of bending moment sign convention, it is hogging, or you can say in moment. So in moments are taken negative, so sign is minus. So this way we are completing our bending moment equation about that section line here. Now as we know, when shear force is 0 means what? dm by dx is equal to 0. Equating this, we are getting the distance x at which the shear force is 0. So we are getting the distance 2.61 meter from C, and I am showing that distance here. So this is distance we are getting. This way we are completing our shear force diagram. Moving to next now, bending moment calculation, same logic. For bending moment, just left and just right is possible only when there is a couple. And observe that there is a point B where couple is acting. So at point B, we are having two values of bending moment, but at remaining all points, we have single value of bending moment. Let us start one by one. Bending moment at A, exactly at A. So there is empty space here. So bending moment at A is equal to 0. Let's move ahead B point, and we know at B there is a couple, so left and right sections are necessary. So first section is bending moment at A, just left. So considering this particular FBD, force intensity is 10, distance is 3. So 10 into 3 is the total UDL acting at midpoint. So this distance is half of 3, that is 1.5. So bending moment is written there. Sign is, it is coming in. So sign is negative. So bending moment B left is minus 45 kilonewton meter. Just right of B. Here I will carry the same value because I am standing on same point. I will carry the same value. Only the point is the couple is coming in picture now. Observe that couple is anti-clockwise this way. In our bending moment sign convention, this indicates in or hogging, and hogging is taken negative. So original value minus 80. The answer is 125. And last point is our C point. Exactly at C, considering this entire portion. So taking moment, intensity 10, distance is 3, and I need distance like this to take the moment. So 10 into 3 is the total load. From section it will act at 7.5 meter and it will create in type moment. So it is negative. First part is over. Now next is couple. Couple is anti-clockwise like this, and according to our bending moment sign convention, it is hogging or in type moment. So minus 80 is taken. Next point is UVL. For this UVL, total UVL is 1/2 into intensity is 48 into distance is 6. Now it will act here. So I need this distance, and that distance is 2/3 of 6, which will becomes 2/3 of 6 here. As it is create in type moment, sign is taken negative. So this way moment at C is taken, and calculating that we get answer equal to 0. Again we get one more check. Bending moment value starts at 0 and ends on 0. So our calculations of bending moment is absolutely correct. One more point we have to calculate, because we know that this is the point where shear force is 0. So at this particular point, what is the peak value of bending moment that we interested to find out. And we have already that equation with us. This equation already we are having that particular section and equation. So in this equation, just put the value of x equal to 2.61. I am getting maximum bending moment which is acting in segment BC. So writing that value here, BC. That means between B right point and C right point, this value arises. So while plotting bending moment diagram, we should take care of these points. Let us plot bending moment diagram. Again baseline is taken. First value is moment at A, this value, it is 0. Second value is B left. So let me plot that B left, it is minus 45. So it is plotted here. Joining this point and B left point, how? Observe that SFD is inclined line. That means degree is 1 or power is 1. For integration of SF, power is 2. So it's a parabolic curve of second degree. Question arises, it is concavity down or up. Remind that table again. UDL is acting downward, then BMD is always parabolic curve having concavity down. So this curve is having concavity down. After plotting 45 on the same point, because of couple there is a sudden rise or fall. Let us see what happens. This value is 1.25. So joining this point and this value down. So that point is already plotted. Next point is C point. But before going to from B right to C, we have one value here. So let us plot that Mx value, which is lies between segment BC. So this is our Mx value. Positive it is, that's why it is plotted above. Now joining this point B right and Mx. Observe that the loading diagram is downward. And what we learned, whenever loading acting downward, BMD is always concavity down. So this is the concavity. So this should be the curve of bending moment diagram. Now next point is C point. Mx is plotted. Now MC we have to plot here. So MC point is 0. So this value. Now joining Mx point and this point. Again there is a UVL acting downward. So BMD has concavity down. So this is concavity down. This way we are plotting bending moment diagram and showing positive and negative sign. But interesting point you observe. Observing BM diagram, do you find any point where bending moment changes its sign or crosses baseline? Yes, it is here. And what is called as that particular point? Bending moment 0 and crossing the baseline. That means sagging to hogging or hogging to sagging. Here it is changing from negative to positive. That means hogging to sagging. That particular point we have already discussed. It is called as POC, point of contraflexure. And this is our fourth step in which we are interested to locate point of contraflexure. For that, we have to extend this particular point and take a section here. You are considering either right FBD, no problem, or you may consider either left FBD of the section to write the bending moment equation. But remind, in segment BC already we have one section taken. Earlier we are having this, and already we are having the equation of that particular bending moment. It is already here. Only what I have to do, this bending moment at this particular POC, it is 0. So what I will do, I will equate this equation to 0, and solving for x, I am getting the point of contraflexure, that is x equal to 4.52 from C, because my section is taken from C here. Correct? So this way I am plotting the shear force diagram and bending moment diagram.